XFEM in Abaqus is a game changer for crack growth simulation, but only if you set it up correctly. Get it wrong and you'll be greeted with everyone's favorite message, too many attempts error. But why does this happen? And why do so many people struggle with XFEM? Because a few crucial settings decide whether your crack will grow as expected or if your simulation will completely break down. Today, I'll guide you step by step through the right way to set up XFEM in Abaqus so you get accurate, reliable results without Abaqus throwing a fit. Let's get started. First, let's define the geometry. The geometry includes the plate and the crack itself. So let's create the plate first. Name it plate. It should be 2D planar, deformable, and let's put this value on 400. We create a simple rectangle just like this. This should be 200 and this must be 100. Enter, scroll button, done, and we have the plate. Now let's create the crack. So from 2D we would put this on wire and we create just a simple line. We assume the crack to be 20 millimeters. Then we have the crack. Now that we have the geometry, let's move to defining materials properties. Materials properties in XFEM is pretty crucial, so watch this section carefully. So I would like to start with the general density, and it should be 1.19 E-9, which is for a polymer, but you can stick to this video even if you're working with the steel. So from the mechanical elasticity and elastic, I would like to have 3240 and 0.35. From mechanical damage for traction separation loss, I would like to have maximum principal stress damage. It's best for brittle materials like polymer and composites. By adding this, we assume if the stress is higher than the critical stress, the crack would initiate. So I put the value of 100 here, and I'd like to have a damage evolution in the sub option, and instead of displacement I would like to have energy. This energy is 0.7. so by defining this one, instead of the material failing instantly, it gradually reduces the stiffness, so we will have an accurate damage growth behavior. Everything is set. It's time to create the section. I'd like to put it on the plate. So from here, create section. The section must be solid homogeneous, even though we're working with a shell plate. If you wonder why, using a solid homogeneous section in this case ensure that the mechanical properties of the material are uniform throughout the plate, enabling accurate representation of how stress concentrates around the crack under uniaxial tensile loading. In other words, it simplifies the setup without compromising the fidelity of the stress analysis. So this section must be solid homogeneous. The material is material 1, and we assign this to plate, and we uncheck this one because we don't want to have too many sets. Done and OK. If you want me to do the same thing for the steels or ductile materials, just let me know in the comments below. The property section is completed, and now it's time to assemble the model. So from here I create the instance. First I create the plate and OK. Now let's translate this. We can select this one to put it just right here and OK. Then auto fit the view. Now create a crack. We want to translate the crack as well. So done. We can simply put it here and OK. Now it's time to go to the step. So we want to create this step. It should be static general. We need to toggle this on because we have large displacement around the crack. This must be 100,000, 0.01, 1E-9 and 0.1. Then OK. The step is not over yet. We need to go to the field output, and here we need to toggle a couple of things on. First we need to go to the state. We scroll down, we should check load XFEM and status XFEM. Then we can close this, and in the failure and fracture we scroll all the way down and we check this too guys. and OK. Now it is done. We're good to go to the interaction. Here's one of the most important part of this simulation. So let's go to the spatial, and from crack we go to manager and create. This crack must be XFEM. First, it asks us to select the crack domain, which is the plate, and we need to check the crack location. So we check this one and we click on this cursor. Then we need to select the crack, and done. So the crack location is created and we set the region. Now it's done. You should see all these green X's all over the material. If you don't see that, something is wrong. Now let's create the final thing here, interaction. From step initial, we need to select XFEM crack growth in order to allow the crack growth in the setup. And OK, now it's time to go to the load to define the boundary conditions and the loading. So first we need to create the boundary condition. I would like to put it on manager, create mechanical symmetry, continue, and we need to select this one, done, and in cast. It cannot move and it's fixed. And we want to create another one, which is the displacement rotation, and I select this one. We should fix it in the X and the rotation in the initial step, but in the step 2 we can have the displacement of 2 mm, so it only can move in the Y direction. So this is over. Many people struggle with the boundary condition and they don't know what values they put here or what sort of boundary condition they should use. And if that's you, comment down below to let me know. I will help you. Now let's focus on meshing, which ensure the accuracy of the model. Meshing is the last step before submitting the job, so bear on with me. We go to the part, and here I would like to put this value on 4. Then we mesh the model. This is a good mesh. The finer the mesh, the higher the accuracy of your model will be. You can go to the job. This is the moment of truth. And if we set everything correctly, we should have a realistic crack growth. Let's submit the job and find out. We say OK, and it gives you the following part have some element without assigned. This is the wire. We don't need the section assignment for this one. So we check yes. This is just a warning, it's not an error. Before jumping into the results, I like to ask you a quick favor. If you're enjoying this video, let me know in the comments. Your feedback helps me improve and create better Abaqus tutorial for you. Now let's go to the results. We click on this one. And yep, we see a crack opening here and grew through the material, and we can see the animation here, but I want to put it on slow. We can have the animation just right over here. We see a crack initiates and we have an opening here. If you have more displacement on the top, you would see the crack can zip through the thickness, and we have 2 separated surfaces. Alright, I'd like to put this on the last increment. And other things, we can have FEM, and I like to talk about this a little. So what is FEM? This is represent the sign distance function for the level set method used in XFEM. It defines how far a point is from the crack surface. Positive values indicate material away from the crack, while negative values indicate material inside the crack. When this is 0, it defines the actual crack surface. When it's greater than 0, the material that is intact and not cracked, while it's lower than 0, the material inside the crack fully separated. Zoom in a little and you can see and compare. The next thing we can see is PSILSM. So what is this one? This stands for Principal Level Set Distance Field. It used to track the crack propagation direction in XFEM simulation. When this value is 0, it defines the crack surface and it determines the principal direction of the crack front, which is right over here. Next thing we can do is to see the displacement, and as you see, the displacement is the highest here, or we can have the option and comment, and from feature edges we can remove the meshes and we can see the crack even better. And here, if we want to exaggerate it a little, we can put the value of 10 for instance here, and we see the crack is in an exaggerated way. Let's see the stress. And here is the stress and the crack front. And that's it. Thanks for watching. If you found this helpful, like and subscribe for more Abaqus tutorial. Want to learn residual stress analysis? Click on the video on screen before it ends. Stay tuned. See you in the next one.